So, hi everyone, and today it's going to be a very interesting session. We'll be starting with ZK, deep dive into ZK and its architecture. And today we have Jeroen. He's a senior cryptographer at zkM. So, over to Jeroen. Welcome and great to have you here.
Okay, yeah, thank you for inviting me. You guys hearing me, please?
Yes, we could hear you.
Okay, good. Yeah, so what I'm going to do today is I want to go into the detail of the definition of ZK snark. I saw that some applications have already maybe been taught, but I would like to get the theoretical setting. Wait a second, something is not as I want. Wait a second. Okay, let me. I had figured out a way not to scroll, but to go back. Anyway, so this is my summary of what I did last time with you guys. And you know, it's not what I want. Anyway, let's do it like that. So the last time I spoke to you guys, I actually gave an introduction into crypto, and I was going to give an introduction to zero knowledge and snarks, but the end was very confusing. So I'm going to repeat some of the things I have said. So one of the problems that we are discussing is how to outsource a computation. So we have a weak client, and we have a strong cluster that that can do any computation. Let's suppose that. So what we want to do is the client wants to outsource a computation, but we want to do this verifiable in the sense that why should the user trust the result? So this is the problem that we are trying to solve in the context of verifiable computation. And what is going to happen actually is this, that we're going to ask the prover. So now you must take care, because now the verifier, the client, is on the right and the prover is on the left. This is somehow almost a convention to put the prover on the left and the verifier on the right. And so the verifier is asking, please compute the FFX. And then the prover is going to say, well, the result is Y, and I'm giving you a witness, W, that this is correct, and the verifier then has a way to verify that. Now, a trivial way to do this is that the prover is going to give the entire execution dump of the program that's been executed. But the problem is that that's not very short. So it's like, it is sort of the trivial proof that the computation is correct. Sometimes it's called like that, the trivial proof. But the trivial proof is very convincing, but it's not very short. So what we want to use a snark, okay? And so what the idea of a snark is the following. It's that it's the same thing, but then the proof and the verifier, they're going to engage in a large collection of messages back and forth. And so the end result is that it convinces the verifier that the result is Y, and there's going to be a succinct witness W. And succinct means that it's short in size and it's easy to verify. Okay, so you can ask, so how can we do that? Well, the trick is, there are two tricks playing in the background here. One is that the fact that the prover and the verifier can interact, that gives additional power. And we also allow for a negligible error probability. So the fact that you allow for small probability of error actually increases the kind of things you can do in computation. And it's actually the case that, sorry about this, it's actually the case that you can prove, because you can have the verifier can do its own computation, and as a result of the computation, send a message to a prover. But actually, we can show that the role of the verifier can be reduced to simply generating random bits. It's sometimes called tossing a coin or flipping a coin. It's like an informal way of saying generating random bits. So this is very interesting, very powerful. These are important results that have been proven 30 years ago. Part is, of course, the famous paper by Goldwasser, Mikali, and Rakov on zero knowledge. So this is yeah. So this is the idea of a snark. Now there's one thing. So a snark. So snarks a priori they are designed with interactions. The way that I show it. Oh, I'm sorry. I'm repeating the same slide. It seems. Okay, so what I'm going to explain now to you is the following. Because a priori a snark is defined with interaction, but then the N of snark means non-interactive. So I'm going to explain to you how we can do that. So here I give like a high-level abstract the description of how such a protocol, an interactive protocol between the prover and the verifier would work. So we have some common inputs, X, and in this case, W now is secret. And so, well, the input, both parties know. Now, in the first step, the prover is going to send a message, which is, of course, it's some function of X and W, and is going to send this message to the verifier. And then the verifier is going to check if it accepts it. And if it's accepted, it's going to create a random string. I don't specify the size here. That's why there's a asterisk here, a star. But this means so let's say of size n, whatever. And so these are random bits, and these random bits is the challenge, and the C2 and the challenge is sent to the prover. And this process repeats itself many times. I just simplified the example to 5 steps. Maybe there are more steps, maybe there are less steps. We don't really know, we don't really care. Because what's going on in if we're going to transform an interactive proof into a non-interactive proof, what we're going to do is the following. Instead of the verifier sending random bits to the prover is going to create these random bits himself by calling a hash function. So this is what we see now in the following slide. It's the same protocol, but what we see is that the verifier, so this is actually, I put this thing in the middle just to show the consistency with the previous slide, but this is sort of non-existent. And in the non-interactive proof, the prover, he creates the randomness by applying the hash function to every part of the protocol so far. And that's really important. And there have been mistakes in the past, serious mistakes of protocol failures in which people did not really apply this idea. But it's important that the randomness that's created here is a result of all the previous messages. So in this case, it's X and M1. Um, Here in C4, it's the everything that we show in here. So X, M1, C2, and M3, and etc. etc. And so, as I said here, we substitute the generation of random bits for a call to a hash function, and this technique is known as the Fiat-Shamir transform. And sometimes people don't even say Fiat-Shamir, they say FS. So if you see this, now you know what that means. It means that um, instead of the prover talking real time to a verifier, he is creating the randomness for himself. And this has an interesting property because the proof now has become completely non-interactive. Okay, it has become non-interactive. It's also, how can I say, it's transferable in the sense that anybody who sees these messages will be convinced that the proof is correct. So this is the essence of the Fiat-Shamir transform. Note that here I say that you don't even have to include, so the prover, what the prover needs is M1, M3, M5. He doesn't even have to include C2 and C4 because the hash function is public, so everybody can recompute the randomness that's needed. Yeah, so this is the end of non-interactive is this. It's the idea that the verifier whose role is only to generate random numbers, you substitute this verifier by a call to the hash function, as you can see here in this step, and you can see here in that step. So this is what's called in general the Fiat-Shamir transform, which is a very powerful transformation. There are some technicalities within it. The security guarantees aren't exactly the same. I don't have the time to delve into this. There's been a lot of recent papers that study exactly the security of the Fiat-Shamir transfer. Okay, so now you know what you should. I hope you understood what I said, that what the N of SNARK stands for. Okay, so now we go on. So what are the desired properties of snarks? So this is again, it is the snark. Well, first of all, we want it to be complete. So what is complete? It means that if both parties are honest, are following the protocol, then the protocol should work as designed. So this is not something very dramatic. It's just saying that things should work as they are supposed to work. Now, soundness is interesting. Soundness is a way to protect the verifier against a cheating prover. It says that if the prover is trying to cheat, then he will succeed only with a negligible probability. So this is important, right? So this is what's called the soundness property of a snark. It says that again, if the prover is cheating, he will be caught with overwhelming probability, so he will succeed with negligible probability. The succinctness, so this is the S of SNARK, the first S. That means that the proof is short and that verification is easy. And I will, in the third part of this talk, I will talk briefly about how do we accomplish this property. And the last property is optional. This is about privacy. Privacy, in this case, is protecting the prover. The prover, it is conceivable that the prover has a witness W, but that it doesn't want to show what the witness actually is. Okay, and so this is called privacy. And now what happens is rather confusing. Oops, I'm scrolling the other way around. I bought a new computer and I struggling with it. Anyway, so here we are. So the original definition of zero knowledge relates to privacy. So zero knowledge officially is about privacy. It's a definition that says that um, the verifier does not gain any useful information from the prover. And I'm going to explain, I'm going to give you examples of this in the next part of the talk. So I'll be giving you the official formal definition of zero knowledge. But what happens is that the marketeers, they well, how can I say? They started to use different terminology. They use zero knowledge to say that something is succinct. But historically speaking, that is not correct. So you have to be very, very careful. When people say zero knowledge, you have to think twice, three times. What do people actually mean? Do they mean privacy or they mean succinctness? And as an example, there are many, in the case, for instance, in ZK rollups. In ZK, in a rollup, the data is already public, so there is no privacy requirement there. The data is on chain anyway. So when people say zero knowledge rollup, they are referring to succinctness. They are not referring to privacy. So this is really, I think, if there's anything that I hope you will understand from the talk today is the abuse of terminology of the word zero knowledge. It's really, it took me 4 or 5 months to understand that when people said zero knowledge, that they weren't talking to zero knowledge in the way that I learned it 35 years ago. Okay, so this is these are the desired properties of a snark. So let me give you an overview of what we've seen so far. I briefly explained to you what is verifiable computation. I explained to you what is an interactive proof. You have a proof and a verifier who exchange messages, and they allow for a small probability of error. When I say small, you must really think small. It's like astronomically small. The chance that you are hit by a meteor today is bigger than the probability that these protocols fail. The succinctness, I'm gonna be talking about it later. So I didn't, let me go again to the S. So SNARK stands for succinct, I explained. Non-interactive, that's the Fiat-Shamir transform. The A is a technical term for knowledge. The AR is an argument, and the K is for knowledge. So this is what we've seen. Now, what we are going to do today, I'm going to talk now about true zero knowledge, okay? And I'm going to do this talking first about authentication using challenge response protocols, give you an example for discrete log, and then give an example using bit commitment and Hamiltonian cycle. And then in about 20 minutes, I should be talking about succinctness as a role of using polynomials. All snarks that we know are all based on using polynomials. So you have to have a little intuition, a little understanding of what it is that make these polynomials so extremely useful. So I'm going on to the next topic. So let's think of a very elementary scenario. We have a client and we have a server, and the client wants to authenticate itself towards the server. And so, well, we all know passwords, but we also know that passwords are very insecure. So to enhance a password, an authentication protocol, you can do the following. You can imagine that there is a password or a secret key K. which is known by the client and which is known by the server. And then as part of the authentication protocol, the um, the server sends a random string C. I call it a challenge. So the challenge that the server asks for the client is to encrypt it. So encrypt it using the secret key K. So this is what the client does. The client um, computes the encryption of the challenge using the secret key K, which results in error. R is the response. And so the verifier or the server gets R, has the key, and I'm going to check if the decryption is equal to the original challenge. So this is like a protocol that says, I know the same key as you do. And so I like this protocol because it is a very intuitive way to explain what zero knowledge is about. What we see in this protocol is that um, the client shows to the server, or the prover shows to the verifier that it knows a secret key K, but this is not sent in plain to the channel. You know, as we can see, there's a challenge, there is a response, but K itself is not sent to the channel. So an adversary who will see this will see the C, will see the R, and must somehow be able to derive K from C and R. And hopefully, supposedly, this is impossible. Now, this is the underlying idea of zero knowledge. And you must even know, I've witnessed the tradition of zero knowledge. And a big part of this zero knowledge was at the same time when people were studying a challenge response protocol. So if we take the previous protocol was using um, traditional symmetric key cryptography. But if I change this to public key cryptography, so you can think of this A is the public key, A hat is the private key, then the verifier or the how I call it, the server knows the public key, and so he sends out a challenge to the prover. The Again, please sign this. So it sends the challenge. The prover uses his private key to sign the challenge, resulting in the response R. R is sent back to the verifier. The verifier now uses the public key of the prover and verifies that the verification indeed results into the challenge as posed. So this protocol is like saying, I know the private keys, right? So the prover is showing that he knows the private key that corresponds to the public key A. And if you think about it, if you know how SSL works, this is how your browser authenticates a site certificate. So in the case, so this is very confusing because the browser now is the verifier. So this is a bit confusing, but because in this scenario of SSL, the verifier is the browser and the prover is the website. So the website has some, I don't know, some certificate for www.google.com, and it has the private key of that. And so the browser will send a challenge to the website, and then the website will sign it, and this will be sent again to the browser. So this is how SSL works. It's only one of the many sub-steps that's inside the SSL protocol, but essentially the verification of browser certificates works in this exactly the way I presented to you. Now, Instead of using RSA, we can do a similar thing using a discrete log protocol. Um, I'm showing this example because it will give us a very clear example of a zero knowledge protocol. So just let me remind you, P is a large prime number. Alpha is some number modulo P, and it should be actually have some special properties that it all that generates all the powers of alpha will all the powers of alpha um, just a second. Amor, eu não consigo dar aula assim. Eu não consigo. Just sorry, somebody interrupted me. Again, so alpha must run through all the numbers modulo P. Then what we do, I'm going to repeat the discrete log problem. So x will be a random number, and you compute alpha to the power x modulo P, which results in beta. And then x is called the discrete log of beta with base alpha modulo P. So this is the discrete log problem. And now we're going to do, we know that the discrete log problem is hard. So it means that if I give you a large prime number, then it's very difficult for you to recompute x given alpha, beta, and p. And so this protocol that I'm showing you now is a zero knowledge protocol, a challenge response protocol for showing knowledge. I know the discrete log x for the equation alpha to the power x is equal to beta modulo p. So, well, first we just sent the parameters. Then in this step, this is the beta that is the statement that's all about. So these are only these two steps are just done only once. Then we're going to repeat the following protocol a number of times. So we recall that beta is alpha to the power x. Now I'm going to create another value called gamma, and gamma will be alpha to the power y, where y is another completely random number modulo p, and gamma is sent to the verifier. Now the verifier is going to toss a coin, is going to say 0 or 1, generate one random bit, and then depending on the random bit, the prover has two options, has two choices. The first choice is that it's going to set r equals to y. Well, y was the random number that it generated. And in that case, if c equals to 0, then the verifier is simply going to check that gamma was computed correctly. Gamma indeed is equal to alpha to the power x, as is stated here. Right? So note the interrogation. The interrogation stands for test, right? In the case that the bit produced is equal to 1, then the prover is going to add the original exponent x from the discrete log problem, add it with y. Now this addition has to be done modulo p minus 1. That's not written, but that's sort of implicit here. And this produces the r. So what you must understand is that it's using the value x. This value of x is being randomized using y, okay? And then in the case that the verifier had sent a 1, then also the verification procedure is going to be different. In that case, it's going to see that, so this r is equal to x plus y, okay? Now, alpha to the x plus y is equal to alpha to the x times alpha to the y. Now alpha to the x is exactly beta, and alpha to the power y is exactly equal to gamma. So the check that verify does is to see that alpha to the power r is equal to alpha to the power x plus y is equal to beta times gamma. So this sort of should convince you that if both parties are honest, then the protocol will succeed. And if alpha is on pardon, so sorry, if the prover is honest and the verifier is honest, then the protocol will work. Now, so this is sort of what I put here. This is the completeness property. If both parties are honest, the protocol gives the correct result, because this assumes that also that the prover can answer both challenges. Well, this is slightly, I'm sorry, I'm running ahead. Um, I have to be more precise. Because completeness actually says even something stronger. You see, the thing is this: if the prover is honest, then it can follow the protocol, and it also means that the prover must know X. Why is that? Because if the prover can compute y and can compute x plus y, then of course it can compute the difference modulo p minus 1. So it shows that it knows x. So this means that if p can answer both challenges, we are sure that the prover knows the value of x. Okay, so this is just saying the protocol is okay. The soundness now is the following. So the soundness is protecting the verifier against a cheating prover. Now, so we have to be a little bit quick about this, but it's like this: if the prover does not know x, then the prover cannot answer both challenges at the same time, because if it could answer both challenges at the same time, it knows X. So if it doesn't know X, it cannot. So it has to, the prover will have to make a choice. Will I do I anticipate a challenge bit which is 0 or a challenge bit which is 1? And if it gets it wrong, then you can show that if it gets it wrong, it will not be able to succeed. So in every round, it has only a probability of 1/2 to succeed. So after k rounds, the probability of success is reduced to 1 minus 2 to the of success is 2 to the minus k. So the probability of being caught is 1 minus 2 to the minus k. And if you do this like 20 times, then this is less than one per million. So this is showing why the protocol is sound. This is protecting the verifier from a cheating prover. You should understand this. This kind of reasoning is very common in many cryptographic protocols. Now we come to the important part of the slide, which is the privacy aspect. So this is related to the traditional notion of zero knowledge, because the idea is that the protocol does not leak any useful information to the verifier. Why is that? Well, in the first, if the challenge bit is 0, then what the prover sends to the verifier is R, and R is Y, and Y is just a random number modulo P minus 1. Well, the prover, the verifier could have produced that itself. So there's there's no information in that. And the same is all true for in the case that the challenge is 1. In that case, the it's the secret, but the secret is randomized with the random value y. And also this is no useful information to the verifier. Now this is sort of a little bit informal what I'm doing. There are official definition of zero knowledge that actually say, well, you know, you can imagine that the verifier has some access to some simulator, and the simulator is doing what the prover is supposed to do. And as long as this distribution of the simulator is the same as of the prover in the official protocol, then everything is okay. So that is very informal, very hand-waving. That is the definition of zero knowledge that you should know about. Yeah, and this is all I'm going to say about zero knowledge. Now I'm going to give you. Oh, okay. So what's the difference? I'm sorry. Oh, no, okay. I'm going to the next point. I'm going to explain to you now what is a commitment scheme. Maybe you've heard of it, but doesn't mind. What's the intuition? The intuition is that you have two parties, the sender and the receiver, or Alice and Bob. Alice commits to some value X such that she can't change her mind. So she commits, but the protocol doesn't allow her to change her mind any longer. And Bob cannot see the value unless and until Alice decides to open. So an example of an implementation is you write the value X on a piece of paper, and you put it into an envelope, and you seal the envelope, and you put the envelope on the table. And then at some later stage, so you have two stages over. You have like the commitment stage, and you have the reveal stage. At some later stage, the one of the two parties decides to open the envelope. So this is one possible real world implementation. You can also write. Imagine that the value X is written on the floor, and you cover it with some opaque tape so that it's invisible to see what has been written there. And then at some later stage, you open, you take away the tape, and you can see what's written underneath. So that these are examples of bit commitment schemes. And here you see like an official model for it. Actually, you can show a commitment scheme. You always need some randomness, because otherwise you can some guessing attacks. You get vulnerable. So here B is a bit, but it doesn't have to be a bit. It can be any string. We even have, you may have heard of it, special commitment schemes for polynomials, because polynomials are so important in the implementation of snarks that we have special commitment schemes for them. So here I show the commitment scheme using the value surrounded by a box. So the box is sort of showing that it's been committed, that is protected. And then you have the open phase. And so in the open phase, the sender sends the bit or the value and the randomness, and then the receiver can check that indeed what he had received before corresponds to the content. So this is a commitment scheme. And I'm going to give you an example of a commitment scheme for a Hamiltonian cycle. And a Hamiltonian cycle is the following. You have a graph, and in the graph, you can go to it's like you visit all the cities. This is the original historical story. You visit all the cities and you come back home. So you go to all the vertices of the graph and you come back. So, and you should know that proving existence of a Hamiltonian cycle is a difficult problem. It's NP complete. So what we're going to do is we're going to represent the graph using its incidence matrix. This is a toy example, and I'm showing you the Hamiltonian cycle. So you go from 1 to 4, they're underlined, right? The cycle is underlined from 1 to 4. From 4, you go to 3. From 3, you go to 6. From 6, you go to 5. From 5, you go to 2. And from 2, you go back to 1. Okay, so this is the cycle that's there, and now we imagine. Of course, this is a small example, so you don't need an interactive proof to show that it has a cycle because the verifier could compute it. But imagine that this is a large example. I don't know, 200 by 200 or 500 by 500. Then verifying that it has a Hamiltonian cycle is definitely not very simple. So now I'm going to show you how you can show in zero knowledge using bit commitments a proof for Hamiltonian cycle. So what we are going to do now is the proofer is going to choose a random permutation on the set of vertices. Okay, so it's going to what vertices, vertex 1 is going to be vertex 2, 2 goes to 5, 3 to 4, etc., etc. And so if you take this matrix and you apply the permutation, you get a different permutation, a different matrix, which is this matrix that you see here. But on top of that, now we're going to apply commitment to each of the cells of the matrix. So we have here 6 times 6 is 36 bit commitments. And this is what I call the commitment H. So this is the commitment, and this commitment now the proofer is going to send this whole commitment to the verifier. And what the verifier does, well, we sort of expected this. It's going to flip a coin, going to send a 0 or a 1, and not very unexpectedly, if the challenge bit equals 0, then essentially what the prover do is going to open all these commitments, right? So it's going to show this the original value of H. It's going to open H completely. It can even show what the permutation was, and then the verifier will verify that this matrix indeed is a permutation of the original matrix. Okay, and still, suppose this is a 200 by 200 matrix that doesn't give any clue about what the Hamiltonian cycle is. Now, in the second case, when the challenge bit is 1, then the proof is going to do something different. Then the proof is going to open one column and one row in every in the committed matrix, and this is going to show that there is an Hamiltonian cycle in the commitment matrix. So it's, and I've shown this here. So under the permutation, the Hamiltonian cycle will also be permuted. So the new Hamiltonian cycle in the new matrix is what you see here. And so you must realize we are seeing here the commitments and their values, but this is not what the verifier sees, right? The verifier only sees something blurred, which can be a 0 or 1, and only sees the opening here. So what the verifier gets is completely useless in the sense of information, but it's very convincing because it shows that the original matrix must have a Hamiltonian cycle. So this is my favorite, one of my favorite examples of what zero knowledge is about. Okay. I hope I made myself clear. Again, the verifier only sees the boxes, doesn't see what's inside the box, except for the positions that have been opened here. And so this convinces that the permuted matrix H has an Hamiltonian cycle. And now we're going to repeat this protocol again 20 times. And then after 20 times, the verifier should be convinced that the prover indeed has a Hamiltonian cycle for the original graph G. So this is an example of zero knowledge proof. I hope you recognize the sort of a common structure. Your prover produces some alternative instance, like using a permutation, using maybe some encryption. The verifier flips a coin, 0 or 1. If the challenge is 0, then the prover must show that the alternative instance is a faithful representation of the original instance. And if the challenge bit is 1, then the prover must show that the alternative instance has the desired property. In the first case, it was showing the discrete logarithm. And in the second case, it was showing the Hamiltonian cycle. So this is a sort of a simplified construction. There have been many protocols that follow this scenario. And I should mention, you may have heard about Alibaba and the cave. This is sort of inspired also on this idea. But I always find that Alibaba and the cave, it sort of hides some of the details, and sometimes I find it more confusing than helping. There has been an important result by my supervisors, to which I also contributed. So because what I do here for Hamiltonian cycle, you can actually do this for Boolean circuits. And there's been a paper by Brassard, Charme, and Crépeau, which uses the same structure as I do here, but it uses for any Boolean circuit. So this is interesting because this shows that you can do it for any computation, except that the construction is hopelessly inefficient because the proofs are not efficient. You also may have heard of Sudoku solutions. So it follows a very similar structure in the sense that you also produce a permuted instance and you commit to it, but the challenge is a lot more, I would say, challenging, a lot more complicated, because in the case of Sudoku, there are many more properties that you need to verify. And so the protocol, instead of having 2 choices, you end up with having, I believe, 27 choices, which also may add to the complication and making it more difficult to understand. So this is my end of what I call true zero knowledge. So this is the official definition of zero knowledge, which applies to privacy. So again, the goal of zero knowledge originally was to protect the prover from the verifier getting to learn additional information. So that leaves me to the last part. I'll be running a little bit out of time, but not more than 15 minutes, I think. Because I want to talk a little bit about succinctness and about how polynomials are used in snarks to do succinctness. There's a conversation I saw with Vitalik Buterin, who says that everybody is a polynomial, and he was referring to this. Everything in snark world, everything is transformed into a polynomial, and we want to show properties of polynomials. So how does this work? And I'm going to give you three small examples of how polynomials are used in computer science. The first one is called Shamir secret sharing, which is, it may seem sort of off topic, but it's helping you to understand what will come later. So suppose that we have a secret that we want to share with three people. Now, if you use a polynomial of degree 2, then this is a polynomial of degree 2. And what we can do, the secret, the constant C will be the secret. We choose A and B in random, and then we are going to distribute shares by giving points of the polynomial. Let me go on to this slide right away. So here you see it's very sketchy draft of a polynomial of degree 2. It's supposed to be of degree 2. And so this here is the secret. And now what we are going to do, we're going to give out, or we're going to compute, so the polynomials of degree 2, as defined above. We are going to give out, we're going to compute f of 1, f of 2, f of 3, f of 4, f of 5, and we're going to send all these shares. These will be the shares of the secret. We're going to send them out to 5 different persons. And the idea then is that, as explained here, so we send out the values for 1, 2, 3, 4, 5. Now, because it's of degree 2, we know that 3 points, they determine exactly a polynomial of degree 2. So any 3 parties now, they can reconstruct f, and they can compute the f of 0. But there is one detail here, because the thing is that you cannot, what I showed here, you cannot do this over the real numbers, because over the real numbers you cannot even define properly what this probability distribution is. But what you can do is you can do it over some finite field, so you can use it like modulo a prime number, where you must make sure that the prime number is bigger than the number of participants, because otherwise you don't have enough values to give out the shares. But that's sort of trivial. So what I'm going to do, what I did, I'm going to use p equals 17. And now what you get is very funny, because if you make a graph of this polynomial modulo 17, it's completely crazy, because over a finite field you have very nice properties of polynomials, but you don't have continuity. So this is something that may surprise you. You do have the algebraic properties of polynomials, but you don't have the calculus properties of polynomials. You don't have continuity. Let me see, does this work if I switch? Yeah, so here, does this work? Yeah, okay, so this is a Jupyter session, and you can see I used Galois, which is something special that's handy for doing all this computational polynomials. And as you can see here, well, actually, I'm running ahead of myself. So what I'm doing, let me go back. Because what I want to show to you is the following. We're going to use this polynomial. So we choose 2 random, we choose 10 random, 13 will be the secret. We're going to to share the secret among five persons. So we're going to compute the f of 1, f of 2, f of 3, f4, f5. And now what want to do is um, we want to reconstruct the secret by any subset of three parties, and the three parties we are going to use are 1, 3, and 5. So there are actually two mechanisms to use this. One is that you use simply you define these equations. So remember, they need to recompute the polynomial. So for them, the coefficients are unknowns. We get A0, A1, and A2. So we set out these equations. These are three equations with three unknowns. And you can do Gaussian elimination, except that all the computation has to be done modulo 17. You cannot do it over the real number. So this is one way to do it. And another way to do it is to use Lagrange interpolation. Lagrange, I'm going to do this very quickly. But Lagrange interpolation is a very elegant formula in which it's sort of plug and play formula, which was already found by the French mathematician Lagrange. What happens is that it's a plug and play formula in which you can you put in the values for the A's, the 3 points on the curve, and then it will give you the final result. So, and this is what I was showing you. I'm gonna skip it here. I'm showing, explaining to you how it works, but for the lack of time, I'm going to skip it. So what you can show is that if you apply that formula, then you exactly get the polynomial that runs through these 3 points. So this is what we are going to do in our example. I even outline here. You can follow if you will have access to the slide, so you can follow all the computations. These computations, you should be aware, they are modulo 17, right? So this is not, you cannot divide them as usual division. You have to do all these computations, and you have to, like here, it's like -2, -4 in the denominator. That's so -2, that gives you 8, but it has to be 8 inverse. So you're going to do that computation. I recommend that for fun, you try to replicate this computation. I think that's a good exercise. And so this is what I was trying to show you in this session, because here is what I do is I'm telling this Galois, I'm telling what the X values are. These are 1, 3, and 5. I tell them what the Y values are, and then I'm telling you what I'm asking him to do Lagrange interpolation. Sorry about that. And so we see here that it results in it gives you all the computation that I elaborately did on the previous slide. This program gives it you in a split second. Okay, so I'm gonna need a 30-second break because something irritates me. Just a second. Okay, so just to put it in context, this was Shamir secret sharing. We showed the protocol for 5 participants, but we could have used a very large value. Doesn't, you can do it for 23 participants. And you also can decide the threshold or the quorum, whatever you want. You want 2 out of 5 or 3 out of 5, or you want 27 out of 50, whatever you want, you can do it. You can use this prime number because this is 2 to the 16 plus 1. You can even do it for any power of 2, but then you will need to understand what a finite field for any power of 2 means, and that is a bit beyond the scope of today's lecture. But so here I do it for general things, so you can take this as your finite field. S can be your secret. So if you have an n plus 1 quorum, then you choose a polynomial of degree n such that n plus 1 parties can reconstruct the secret, right? So what you do, to distribute the secret, you evaluate f at m distinct points, and you send out these shares, and then any subset of n plus 1 shareholders can reconstruct f. Okay, so this is Shamir secret sharing. What are the properties of polynomials that we need? Well, polynomial is just a formal object of degree n over some finite field. It has all these n plus 1 coefficients. Let me scroll. This is easier if I oops, here. Okay, so it's specified by n plus 1 coefficient, and also if you have n plus 1 points on the polynomial, then you also can uniquely know what polynomial is. All right, so this is the generalization of what I said. Three points of a 2-degree function define the polynomial. This is in general the case. And it's important to know this terminology. If you go from 1 to 2, okay, so if you have the polynomial specified as coefficient and you want to evaluate it in point, that's called evaluation. And if you go from 2 to 1, then so you have n plus 1 points, then you want to go back to the original representation, then this is called the discrete Fourier transform. This is called interpolation. I'm sorry. This is called interpolation. So you can use Lagrange interpolation, which is what I just showed you. If you choose your points very cleverly, then you can actually do better. You can do n log n, and will be the discrete Fourier transform. There's a lot of details here, but unfortunately I won't have time to discuss that. So now I want to talk about a second application of polynomials. So now suppose that well, my field here is what you see here. So these are like, let's say these are 16 bits. So I have 8 symbols of 16 bits. So now what I'm going to do is the following. I have my message, which consists of 7 words of 16 bits, and I'm going to interpolate a polynomial that's going through all these points, and then I'm going to compute all the values of the polynomial at y8 at the well, how do I say it? So at x equals 8, x equal, and I'm going to it gives me as a result y of 8, y of 9, up to y of 39. So what you must understand is the following. It's like the message here. The message here is 8 eight words of 16 bits, and I'm going to represent it. I'm going to expand this message by a factor 5, right? And I'm going to expand it using a polynomial by interpolating the polynomial of degree 7 over the whole interval. Okay, that is what I'm going to do in this example. And um, we use this as a way to correct errors, because now the idea is the following. Um, if somebody, the idea is that you send this message, which is 5 times longer, you send it over a very noisy channel. And the idea is the following. As long as the receiver receives at least 8 messages, any of these 40 messages, of any of these 40 messages, it receives 8 messages, then this message define a unique polynomial, and so it can compute the polynomial and it can reconstruct these 8 original values of y, and it can reconstruct the original message. So this is a way of using error correcting. Here I generalize it to arbitrary values. So in my example, I had n equals 7 because I want n plus 1 to equal 8. No, I'm sorry. No, that's correct. And n equals 7 because we are starting from 0, so we have 8. And m will be the expansion. And so in the example, I used m equals to, well, 39 because that's 40 minus 1. Okay, it gets a bit ugly because of the zeros. And now what we can see here is that there are two kinds of error corrections. We can have erasures. So an erasure is if something gets lost. You know, a point gets lost, but you know which is the point that gets lost. So then you can recover the message as long as you have sufficiently many points. In the case of errors, then it's more complicated because then you may receive something, but you may not know if there is an error. And then the sort of rule of thumb is that for every error that you have, you need at least 2 correct points. And maybe you have heard of this. So these actually these codes using polynomials, they are known as Reed-Solomon codes, and it's very interesting if you look for this. All RCDs, DVDs, and even QR codes, they are based on this whole philosophy of you take the original message, you extrapolate, you extend it to with a polynomial. So it means that if you use you represent the original message in a larger space, and as long as you get sufficiently arbitrary values in this larger space, you get them correctly, then you can reconstruct the original message. It has also been used in NASA space missions, so it's really very interesting. Reed-Solomon codes are just by itself worth a complete talk, because there are no codes that are implemented in billions of equipments or have been sent to the other side of the universe. So Reed-Solomon codes are very interesting. Now, the final thing I would like to explain to you is this. So in the previous example, if you remember the previous example, we had the original message was um, eight 16-bit values. Now, if you change one bit of these values, then what happens is that the polynomial that you have, it will be completely different. So the original polynomial will be completely different, and as a consequence, the redundant values that are, um, in this case, are y8 until y39, they will completely different. So I want to show you this in, again, I made an experiment in IPython to Python. So this is the thing that we hear. Here I redefine the field. Here I define the values of x on the first interval between 0 and 7. Now I choose the y values, I choose them completely random. And then here I tell this Galois packet to do Lagrange interpolation to compute the polynomial who's so and so. So the like the x value here is 0 and the y value is this one, and the x value is 1 and the y value will be this one. And so this is the polynomial that will go through all these 8 points. And then what I did is sort of useless, but then I interpolated the polynomial in the range from 0 to 39. So these are the values that you can check. Of course, this value should be equal to this value, and etc. Um, and now comes the interesting part. So because what I'm going to do, I'm going to add, just change one bit. So what I'm going to do is I'm going to increment the y value. So the y value is this one. I'm going to increment it from 72 to 73. So this is what you will see here. It's incremented from 72 to 73. Now I'm going to again interpolate the polynomial, and well, it's not obvious, but this polynomial is completely different from this polynomial. Now you can't see that, but of course you can check that. So what I did was that I made a script here in which I compare the first polynomial f with the second polynomial g on the whole interval. And what we see is very amazing. We see that the only values in which the polynomials agree are the defining values. So what does that mean? It means it is a way for us to amplify errors. So what does that mean? It means that suppose that the prover verifies, no, I have a problem. Let me, oh, I went to the wrong application. Safari. Okay, I'm back. I clicked on something wrong here. So let's see what's written here. If you change one bit of y, then the interpolating polynomial g will be different. So the extension polynomial g will also be different, right? And why is this interesting? Because this is a way to do verifiable computation. We can now use polynomials in the following sense. The prover, remember, the prover is the guy who has all the computational power. So we can ask the prover to do this kind of computations, as it's explained here. In order to catch a dishonest prover with little effort, the verifier tests on the extension domain whether the f of x equals to the g of x, as in the previous example. And in order to do that, the verifier is only to verify that f and g are equal on the interval of 8 until 39. Or even as I said here, you don't have to stop at 39. You can make the 39 as large as you want, as long as you stay within the size of the field. So this is, it's sort of simplified, but this is the underlying central idea of snarks. We are converting everything into polynomials because it allows us to catch a cheating prover. If it allows us to catch a cheating prover in a cheap way. The verifier only has to check one value in some large domain and verify if F and G are equal. You can even compute the probability. It's in this formula. Um, because you can show the following, that if G is equal to F, is not equal to F, then we know that they can agree on at most n points. Because if they agreed on n plus 1 points, they would have to be equal. That is the consequence of what we've seen before. So we know we have a limit on the number of points on which they can be equal. And so we can control the error probability by playing with these parameters. And remember, n is the number of original points, m is the size of the extension. So we can control this this probability. So this is a very important formula for snarks. It's a kind of basic snark, but it's very important. Yeah, and that is essentially it. I forgot what. Oh yeah, I just. It turns out that this is sort of, well, it turns out that in the example that I showed to, we saw that this n divided by m actually it turned out to be 0, right? Well, it turned. No, I'm sorry. No, it turned out to be n minus 1 divided by. Forget that. Um, I hope you got the idea. The idea is that all these snarks, they are based on this idea of extending polynomials. As I said before, the extending polynomials, they have been used already for ages in error correction, which are called Reed-Solomon codes. So if you see Reed-Solomon codes, you only have to think, oh, these are polynomial extensions. You don't have to worry too much about that. But the difference is that we don't use it. It's sort of counterintuitive. We don't use it to correct errors. We use it to amplify errors. So again, why would you want to amplify errors? Well, because we want to detect cheating prover. So that is the idea, the underlying idea of a snark. So now I get to the conclusion of today. Again, I told you what's called zero knowledge actually isn't zero knowledge. Verifiable outsourcing of computation has many applications beyond rollups, but the foremost application of all these zero knowledge protocols, the motivation at the moment are the rollups. Cryptographers are in high demand, if you hadn't noticed that already. Multi-party computation and homomorphic encryption, I understand that other professors will take care of that. So this is where I want to stop. Thank you very much for your attention. And I'm so glad there were no interceptions today, unlike the previous talk. Thank you very much.
Yes, this was taken care of. Thank you, Jeroen. Do you have time for one quick question?
I do.
There was a question about the commit reveal protocol. If you can give an example of where this is mostly used, or which scenarios where this is more helpful.
Oh, it's much more helpful. So I skipped that. I often, if I have more time, I usually show that.
Maybe just a quick example.
No, yeah, I've got to be quick. I just want to scroll back to just to show to the context. Commitment binding. Well, let's show this one. So one thing that you can do, well, no, it's better to show this one. So one thing you can do is you can do it to do a coin flipping protocol. So Alice and Bob, they want to agree on a truly randomized coin. And one way you can do it is this. So the sender commits to a 0 or a 1 and sends it to the receiver. Okay, and then the receiver just sends a random 0 or 1 to the sender, and then in the third step, the sender opens the commitment, and the resulting commitment will be the exclusive, or the resulting coin toss will be the exclusive or of the 2 bits. And now, why is this honest? Because well, you know, the receiver sends, no, the receiver cannot see what's inside the commitment. So from his perspective, the contribution of the sender is random. Now, of course, at the moment that the receiver, or let's call it Bob, if Bob sends his random coin toss to the sender, then the sender already knows what the coin toss is, but the sender cannot change his mind. So this is sort of a very quick explanation. If you look at the original coin flipping protocol by Manuel Blum, then it's based on a commitment scheme. So Alice commits to a random bit. Bob sends a random bit. Alice opens the bit, and both parties agree on the exclusive OR of the 2 bits, and that is establishes an honest coin flip, an honestly generated random bit. So this is already a very basic, simple application of commitment. There are many applications of commitments beyond zero knowledge proofs.
Right. Yeah, thank you so much. It seems like it's such an easy protocol, but it can be used in so many different blockchains.
It is. It used to be, yeah, well, it's always handy. And like 30, 40 years ago, people just study bit commitment for several years. And there are many papers written about it.
Right. All right. Given the time, again, Jeroen, like always, thank you again for spending this time for the zkMonk community. This was a great session, great learning. So I really appreciate your time. Thank you again.
Yeah, thank you. You're welcome. And good luck tomorrow. It's Lucas,
Bye.
I think. My
Yes,
colleagues are
tomorrow is
going to
Lucas.
take over now. Okay. Bye-bye.
Correct.
Bye-bye.